Hello everyone, welcome back to the channel. I hope you guys are doing amazing. So let's see today's daily challenge on Leetcode. It is a quite interesting problem today. So let's see. Number of subsequences that satisfies the given sum condition. The problem statement is simple. You are given an integer array nums and an integer target. Return the number of non-empty subsequences of nums such that the sum of the minimum and maximum element on it is less than or equal to target. Since the answer may be too large, return it modulo 1e9 plus 7. So target 9 means that the maximum and minimum value in your subsequence, whichever subsequence you are selecting, the maximum and minimum value, the sum of those should be less than or equal to target, and the number of such subsequences we need to return as output. Okay, so number of subsequences. You see, we select 4 subsequences here, and in all of them, the maximum plus the minimum value is less than or equal to 9. Is less than or equal to 9. You see, it's 6 here, 3 plus 3, it's 8 here, it's 9 here, it's 9 here again. So 9 here again. So I hope you understood the problem statement, what we need to do exactly, and the nums dot length is 1e5. So we need to solve it in O of n or O of n log n. So what is the number of subsequences that satisfies the given condition? So let's try to see how we approach this question first. Okay. So first of all, I will tell you something about how to count the number of subsequences. Okay, so if I was hoping that you will know this, but I am not assuming anything. I will tell you that if you are given an array of length n, okay, and you want to just count number of subsequences, okay, number of subsequences, it may be empty also, okay, number of subsequences, then what will you do? What will you do? So you can, in your answer, in your subsequences, whichever subsequence you are selecting, you have two choices for the first case. Either you will take the first element or you will not take it. Okay, similarly you have another two choices. Either you will take the second element or you will not take. So in this manner you have 2 to the power n choices. Okay, so number of subsequences, if anyone asks you what is the number of subsequences of an array of size n, you will tell it's 2 to the power n. And if you know, select every time, if you select something like no, don't take, you will get an empty subsequence. Okay, so if anyone wants to ask you the non-empty subsequences count, then you just subtract -1 from it. Okay, so that's not what is required here. So but this result you must know, okay. So let's see now. Let's come to the problem. Okay, so what was the problem? We need to count the number of subsequences. So let's say we have something like this: 1 6 8 9, okay, and then 2 3 4 4, and let's say 5. Okay, so I have these elements. Now if I want to ask you that you select a subsequence where the maximum element is 1 and minimum element is 6, and you want to find the count of all the subsequence. If I am trying to ask you only this, okay, then what will be your answer? Then you see, if you select 6 as the minimum element, 1 as the minimum element and 6 as the maximum element, then you can select the subsequences. In your subsequences, you can either decide whether to take or not take this 2, this 3, okay, and this 4, this 4, this 5. Okay, so you see, everything in between 1 to 6 you can take, everything in between, and whichever is more than 6 like 8 and 9 you cannot take, because if you take that, the maximum value will change to you can see I did a mistake here. This is maximum is nothing but 6 and the minimum is 1. So if you see, then if you take something like 8 or 9, it will exceed the maximum value. So maximum value 6, that will be violated, so you cannot take 8 or 9. So what did you understand from this? If you are fixing the minimum value, okay, and the maximum value also maybe, okay, then you want to find all the subsequences. Let's say you want to fix 1, okay, let's say you want to fix 1, and you want to find all the subsequences that has the minimum element as 1 and the maximum element does not exceed 6. So you can take everything that is between 1 and 6. Okay, you can take everything that is between 1 and 6, and you cannot take anything which is above that. So this gives you the idea of sorting. Okay, this gives you the idea of sorting, and this also tells you that even though subsequences means relative order is maintained, sorting will ensure that it is not hampered, because you see, let's say we sort this. We will then have 1 2 3 4 4 5 6 8 9. Okay, now you will get everything between 1 and 6, you will get in between. Okay, and everything else you will get outside it. So this is from there only you get the idea of sorting. And the thing is that you might be thinking the relative order is hampered and so on, but you see, we care only about the maximum and element, only about maximum and minimum element. Okay, the catch is this: we care only about the maximum and minimum element. So the maximum and minimum element should be the same, and the sum of that, we should try to make it within that value of k, which is target. Okay, I'm taking k as the target. So if you try to now solve it, so first you get the idea that you need to sort it anyways. Okay, so now let's say you have something like k equals to 9. Okay, so you want to ensure that your maximum and minimum value, the sum of those should be less than equal to 9. So what can you tell? What can you tell? So let's say you are trying to, first you have sorted it. Okay, very good. Now you tell me that if you are selecting, okay, so understand this in very much detail. Okay, if you are selecting 1 as the minimum element, okay, then for k equal to 9, then for k equal to 9, what is, okay, what is number of subsequences? You just answer me this question. Try to pause the video and answer these questions. Okay, so if you see, if you are selecting 1 as the minimum element, you keep one pointer here. Okay, and another pointer, you just iterate through this array unless you get something. Let's say you have a I pointer here. Okay, and you iterate another j pointer, and you will reach 8 with that j pointer. Why? Because you will do something like while this array of I plus array of j is less than or equal to this target k. Okay, that target value k and j plus plus. You will do like this only. Okay, in order to find the maximum such subsequence. And if you are selecting 1 as the minimum, then j is the maximum value which you can go till maximum value. Now the maximum value can be 8, can be 6, can be 5, can be 4, can be 3, anything but not 9, because then 9 plus 1 will be 10 and that case will be violated. Okay, then what you need to do, then what you realize, you do that if you are selecting, let's say 1 only, so you have something like 1 2 3 4 4 5 6 8, you have the I pointer here. Okay, and you have your j pointer here. Now I pointer, you see, you want to select a subsequence as 1 as the minimum value. So 1 you are always taking, and then you are asking yourself whether you will take or not take this value. You have two choices for this: whether you will take or not take this value, whether you will take or not take this value, whether you will take or not, and so on, whether you will take or not take the last value. Okay, so what did you get here? Did you get something like 2 to the power of j minus I? Okay, you get something like this. Okay, so that's how you understood that. So let's say if you are confused how j minus I, you see, if I is, let's say, 0 here and j is, let's say, 2 here. Okay, so you want to take only within these two elements. So 2 to the power 2 will be the answer. That's 4. That is nothing but 2 to the power j minus I. So that's just your own calculations. I'm just telling you that. Don't worry about it. So you get it. How I, it's 2 to the power j minus I. So you see, in this case, the 1 was the minimum element. Okay, 1 was the minimum element. Now, what if I tell you in the same array, now keep 2 as the minimum element, as minimum. Okay, what you will do now, now 8 plus 2 is becoming 10. Now you realize that uh, if I exceed my I pointer, then I need to shift my J pointer also to the left, because now I value is decreasing. So you see, array of I plus array of J, initially it was k, right? It was less than or equal to k. But if this value increases, in order to maintain the stability, you might decrease, you might have to decrease this value, you might have to decrease this value. So you just check that how much we need to decrease J pointer. So you see, when you take 2 as the minimum value, you just do this while loop again. As I told you, this while loop, while array of I plus array of J less than equal to k, now greater than equal to k, right? You will do J minus minus. Okay, you will do J minus minus, and you will back your J pointer to point it to, let's say, initial, now it's point, I pointer is pointing to 2, and then now J pointer should point to 6, because 6 plus 2 is 8, which is less than equal to k, which is 9. Okay, so I hope you now understood that. Then you see something like this will come, 1 2 3 4 4. What was the whole array? 1 2 3 4 4 5 6 8 9. Okay, so 5 6 8 9. So now you have the I pointer here, and your J pointer should move from here to here, from 8 to 6 it should move. So now you have array of I plus array of J is nothing but 8, okay, which is less than or equals to 9. So you have it. Now keeping 2 as the minimum value, you can just do it. Okay, you can just do it, and you also realize that the number of subsequences now will be nothing but you will fix 2. Okay, and for every other cases you will have two choices. So again, you have 2 to the power J minus I. So similarly, you keep 2 as the minimum, now keep 3 as the minimum, and you just go on, and you just go on. Okay, you just go on, as long as you do not exceed this J pointer. Okay, as long as you do not exceed this J pointer, just keep going it, keep going it through. Okay, so and you will realize that you have got your answer. Now we also need to do something known as binary exponentiation here, because you see, you are doing modulus answer plus equals to something like 2 to the power J minus I. I will show you how this is happening. But if you tell something like 2 to the power 80, we need to calculate some mod value, right? That is possible always, but 2 to the power 80, if you try to calculate, it will not fit even in long. Okay, it will not fit even in long. So you need to do some binary exponentiation, which is also a fast method to perform exponents value, and it will help you to get the mod. Okay, it will help you to get the mod. So let's see what is that. I will also explain you that. Don't worry about it. So let's first try to approach the problem. Let's try to approach the problem at first. So you'll see, we'll get something like n equals to nums dot size, and we just sort the nums. As I had already told you, the intuition behind why exactly the even after being a subsequence, it is not violating anything, because we are only bothered about the first and the last element. So we have now sorted our answer. So I will use 2 pointers. Okay, I0, and let's say we use something like J0. Now, first of all, for initially we need to set the I and J pointer to the extremum values, such that it does not violate the target K condition, and then we need to shift the J pointer one by one to the left. Okay, so first we initialize I and J as 0, and I will tell you that while J less than n and array of I, not array, we have nums here, nums of I. Okay, you have something like nums of I plus nums of J is less than equal to K. While this condition holds true, you just keep incrementing your J. Okay, you just keep incrementing your J, and in the answer, you also have an answer. Okay, int answer is 0, and I will keep a mod as a global variable, int mod as 1e9 plus 7. That's what it is told to do. So what I will do here is that I will just add answer plus equals to answer plus something like power of 2 to the power uh, J minus I. You see here, j will be nothing but exceeding one element. Okay, so that's why j minus I minus 1 will be there. If you did not understand, I will explain you just a second. I will just put this bond. Uh, okay, so what did I do? Why did I do minus 1 here? Because you see, at first I am incrementing j, right? So I am incrementing j. See, for the first iteration only, this is true that if I am doing something like this 6, 8, 9, and k is 9. Okay, I start I equals to 0 and j also 0. Okay, from here I start I and j. I want to increment j unless the criteria this plus this is holds true. Okay, so you see, when I reach here, 1 plus 8, that is still less than or equal to 9, which is k, right? That's still less than or equal to k. So that still holds true. So I will increment j again. I will increment j again. Uh, so j will have one extra value. So instead of the 2j minus I, 2 to the power j minus I do j minus I minus 1 to get rid of that extra value of j. And you see, we also need to take care that if somehow j becomes n, we will be facing trouble in from the next iteration onwards, right? Because as I told you, j should point to the number according to our calculations. We were applying this formula, and j should point to the element to the last feasible element where array of I plus array of j is less than or equal to k. So the last feasible element it should point. So it should not exceed something to which is greater than n. Okay. So if it happens that j equals to n, you just do j minus minus. Okay, you just do j minus minus. Now I will do a for loop. I have already taken care of the first element. So this is nothing but number of subsequences taking first element as minimum. First element is nothing but the global minimum. Okay, you have sorted only. So first element is on nothing but the global minimum. So this you have counted the number of subsequences taking the first element as minimum. So now you want to count starting from 1. Okay, and this will be nothing but less than n and I plus plus. Okay, so what you need to do now? You need to do a while loop. You need to decrement j, right? Now you need to decrement j. So while you do, uh, you need to take care that I should be greater than equal to j. This criteria must hold true. And nums of I plus nums of j till the time it is greater than k. Till the time it is greater than k, do j minus minus. I hope you understood this. I am doing nothing but as I told you here, I am decrementing j from 8. I am just going to 6 uh, because 8 as I incremented I, now I went from I equal to 0 to I equal to 1, and I will go I further also. But as I increment I, every time I should see that it should not violate the criteria, and if it is violating, I should decrementing j unless it does not violate. So this is the violating criteria. So if it violates, I will decrement j. If it violates, I will keep decrementing j. That is the intuition. So you get this. Okay, you get this. Now I will tell you that after decrementing all of the j, if still I is still greater than or equals to j, if this still holds true, then only we do something like answer equals to answer plus power of 2 to the power of j minus I. So I have already explained you why I am doing j minus I here. So I will not explain you again. 2 to the power of j minus I. Okay. Now I have this. And if I see now, I just need to return the answer. Okay. I just need to return the answer. And I think we are done. Do you think we are done? So as I told you, this power function will not work. So let me show you also. Let me show you. If I try to run this, uh, you see this will be something like invalid operation to binary exponents binary expression. So this by default, does it return something like double or something? is that it will be problem with this power function only. Okay. So you need to write some binary exponentiation thing. Okay. So as I already explained you that this 2 to the power 8, if you're trying to store, it will give you error because it is a very long thing. It is a very long value. It should not, I mean, uh, it will not even fit in long. So what you can do, you cannot do anything. So you need to use something known as binary exponentiation. So if you do not know about binary exponentiation, let me just tell you. Okay, binary exponentiation. Uh, you want to calculate a to the power b in a very fast manner. Okay, and in every time you will get modulo also. This works even if b is something like 1 in 9. So you will be surprised that you cannot even multiply a b times. If a is b is 1 in 9, you cannot even multiply a 1 times, because even if you use a single loop, it will give you tle. 1 in 9 does not work. You don't know that, right? So this will not work. So what you do, you try to do something in binary. So uh, you see let's say we are calculating something like uh, let's say 6 to the power of 11. Okay, a is 6, b is 11. Now if you try to write 11 in binary, 11 is in decimal. If you try to write in binary, what it will be? 0 1 0 1 1. Okay, I guess you know this already. So can you write this as 2 to the power 3 plus 2 to the power of 1 plus 2 to the power of 0? Can you write it something like this? So it is nothing but 8 plus 2 plus 1, which is making up 11. So you can also tell me that uh, this 6, I can write 6 to the power 11 as nothing but 6 to the power 8 into 6 to the power 2 into 6 to the power 1. So you can tell me that I am writing it this way. And you see, so it is possible to write in all the powers of 2 only. So what you will do is that you will keep a result. You will keep a result as 1, and you will keep another multiplier, okay, which you will multiply every time. So initially your result is 1. If now you will iterate through the bits of this power. If it is 1, you will multiply the multiplier. If it is 0, you will not multiply it, because you see 0 2 to the power 2, this was supposed to be 2 to the power 2, but it's 0. So 2 to the power 6 power 4, that term is absent here, so you don't need to multiply here. So, okay, so how that's coming, let's see with this diagram. uh, if you have the multiplier as something 6, and you multiply this 6 to this, you get, so you see the first bit is 1, so you will definitely multiply this 6. Okay, you will multiply this 6 and you will get 6. Okay, and then what you need to do is that the multiplier here was 6, but now you need to change it to 6 square, and then to 6 power 4. Every time you just need to square it, then to 6 power 8, and so on. You just need to move it irrespective of whether it's 0 or 1. You just need to move the multiplier. Now you check that the second bit is also high. Okay, the second bit is also high, so you multiply this multiplier. Okay, you multiplied this to get 6, right? Now you multiply this, so 6 into 6 square, it becomes 6 cube. Okay, now you see the next bit is low, so you do not multiply this, you keep it 6 cube. You do not multiply this. Now you see another bit, you traverse to the bit and see that it is also high, so you multiply this. Since it is high, you just multiply this. Now 6 power 3 into 6 power 8 will be 6 power 11, and you will end up in getting your answer. So this is how binary exponentiation works. You just, what you do is that you just keep, to get the last element, you just keep right shifting it. Okay, you just keep right shifting it, 1 0 1. So you will get these bits in order. These are the bits, the first elements. You will get this in order, 1 1 0 1 1 1 0. You just right shift every time, and you just perform your binary exponentiation value. So I will write a function. Okay, I will write a function, binary exponentiation, which will take this, which will perform this, and it will return nothing but a to the power of b. and it will do a modulo also. So as I told you, I need to keep a result as 1. Okay, and while b is greater than 0, while b is positive, what you do, you just right shift b. As I told you, you just right shift b by 1 element. Okay, and if you see that if the last bit is high, so how you will check that? B and 1, you perform an and with 1, and you just check that the last element is 1 or not, last bit is 1 or not. If it is high, then you do something like result equals to result into this a. Okay, you do this a, and you just do this long and also perform a mod. Okay, to perform this mod, and every time you need to change the a value, you need to change the multiplier, right? So this multiplier you are changing every time. 6 square 6 cube, so you are doing every time, so you are squaring it every time. So a equal to a into a, this thing you are doing every time. And since mod value is there, you need to put mod at all costs. You cannot afford to miss it. Okay, so you see you have this now, and you just return your result. So if the bit is high only, I will multiply my multiplier, and every time I will just right shift and keep squaring my multiplier. So you, in this way, I just calculate binary exponentiation. And if you try to run it now, it should work, but there might be some error. So let's see. So you see, it is showing some error. So we have some bug in the code. Let's try to see. Let's try to visualize it. Mm, So you see, I am missing out one base case here is that what if the first element sum is only greater than the target? Then you don't have any answer only, right? So if you have something like nums of I plus nums of 0, so it's 0 0 initially, but what if initially only you don't have any answer? What if that initial sum is only becoming greater than the target? You just return 0, you don't have anything to do. You just return 0. Okay, and I also did a mistake in telling that j is greater than or equals to I is greater than or equal to j, because it will be j greater than I, because j is the right pointer, right? So it should be greater than or equal to I, so that is quite obvious. So this is a mistake which I did. So if you try to run now, you are getting a TLE also. So you see, I just changed this condition, but I did not change this. So now if you see, so you see we have the accepted case. If you try to run it, uh, so you see, you have the accepted thing. Okay, so that was all for this problem. So what if, can you optimize it a little bit? If you see, uh, if j is greater than or equals to I, then you do this. But j is already right pointer, right? It cannot go towards right any further. So if it's false, can you break it? Does this work? Does this right work? And does this return anything greater? Does this improve your time complexity? A little bit, it just improves little bit. So this is more or less not that much deterministic. Okay, it's not that much deterministic. So yeah, that's all for this video, I guess. So yeah, I hope this was a medium kind of problem for today, but I hope your day is going to be really easy. Thank you so much.